Hello, my name is Paul Geyer, and I'll be talking to you today about heating, ventilating, and air conditioning systems. This is how I will be talking about things today, kind of the chapters in the book, you might say. First, some introductory comments. Then chapter 2, we'll look at load calculations. 3, air conditioning equipment. 4th, air distribution. Chapter 5, some little rules of thumb. And chapter 6, heating and cooling media distribution. And this, I want to emphasize, is an introductory presentation. This is not for mechanical engineers who have been engaged in the design of HVAC systems for decades and are looking for a in-depth discussion. That's not what this is, and the topic is so broad that it would be impossible to explore it in great depth in the relatively short time that we have to chat. By way of introduction, this will tell you a little bit about me. For 35 years, I was what I characterize as a straight-ahead designer, cranking out drawings and specifications for the construction of buildings and related infrastructure. I got registered in a few different things along the way. I'm basically a mechanical engineer, and the largest percentage of the design work that I was involved in was HVAC systems. This is an introduction to air conditioning systems, frequently referred to as HVAC systems, heating, ventilating, and air conditioning. It's intended for those engineers, architects, and construction professionals who are only peripherally involved with HVAC systems in their professional activities, but would like to learn more about HVAC concepts, principles, systems, and equipment. It's not a design manual, but will give design and construction professionals a step forward in understanding this area of building technology. Design information presented here is in a manual form. That is, calculations are presented as if calculated manually, although of course this is done in most cases in practice by computer programs. This manual presentation will, I believe, give a better understanding of the underlying principles rather than just leaving the matter of load calculations as a simple data input exercise. This is an introduction to air conditioning systems, frequently referred to as HVAC systems, heating, ventilating, and air conditioning. It's intended for those engineers, architects, and construction professionals who are only peripherally involved with HVAC systems in their professional activities, but would like to learn more about HVAC concepts, principles, systems, and equipment. It's not a design manual, but will give design and construction professionals a step forward in understanding this area of building technology. Design information presented here is in a manual form. That is, calculations are presented as if calculated manually, although of course this is done in most cases in practice by computer programs. This manual presentation will, I believe, give a better understanding of the underlying principles rather than just leaving the matter of load calculations as a simple data input exercise. The first step in HVAC system design is to select indoor and outdoor summer and winter design conditions. There are various sources of this climate information, but two that are available, and they are free, are produced by the Department of Defense, the Corps of Engineers specifically, and the Naval Facilities Engineering Command. These climate data publications there's nothing governmental or bureaucratic or military about them. They're just good, solid technical guidance, and they are available free. First, with regard to heating load, Heating load is the amount of heating that must be provided given the assumed outside air temperature and the desired inside air temperature. It's calculated as described below, and heating load is due to transmission, infiltration, and ventilation. Transmission heating load is calculated using equation 2.1. Q is equal to U times A times TI minus TO. Q is the heating load in BTUs per hour, and BTU stands for British thermal units, and that is the unit of heat that has been used in the air conditioning, the HVAC industry for many decades. It was originally defined back in the Industrial Revolution days in the late 1890s in Great Britain. U is something called a heat transfer coefficient, and this is simply something that is looked up in a handbook for the particular wall, floor, or roof construction that you have in your building. A is the area of the surface, wall, window, or roof, depending upon what it is you're calculating the heating load due to transmission through. T sub I is the inside design temperature, and T sub O is the outside design temperature. This formula is used to compute the heat transmission losses from each element of the building's skin. Note that attic and crawl space and ground temperature are different from outdoor temperatures. In addition to the heating load due to transmission, there is heating load due to infiltration and ventilation. Infiltration is outdoor air that gets into the building inadvertently, and it is in the winter cold, and that air has to be heated up, and that becomes part of the heating load. Ventilation is outside air that you intentionally bring into the building for air quality purposes. Outdoor air provided for ventilation sometimes is required to exceed the air exhausted by 10 to 15% or so, which creates a positive air pressure inside the building, and this tends to offset the infiltration air. But this can create problems with when you have a positive air pressure, with doors slamming and being difficult to open and close, and so on and so forth. The formula for calculating the heating load due to infiltration and ventilation is equation 2.2. Q is equal to 1.10 times CFM times TI minus TO. 1.10 is just a constant that we won't go into the derivation of. TI is the indoor temperature and TO is the outdoor temperature. So now typically a comfortable indoor temperature is around 72 degrees Fahrenheit. And by looking up the appropriate climate data, you might select an outdoor design temperature for the winter of, say, 20 degrees Fahrenheit, something like that. CFM, of course, is the cubic feet per minute of outdoor air that is coming in by ventilation and infiltration. And Q, the heating load, is the sensible heat load in British thermal units per hour. The term sensible, there is sensible heat and latent heat. The latent heat of air has to do with the moisture content of the air, and in many locations in the United States you can ignore latent heat. The sensible heat is when we talk about heat loss. When I talk about heat loss, I will be talking about sensible heat loss. If you're designing an air conditioning system in a very humid climate, and there are humid places in the United States, Florida, some of the East Coast, that sort of thing, but the largest part of the US, you can ignore the latent heat. This calculation does not apply to industrial ventilation systems such as shops and things like that where you are intentionally exhausting large quantities of air from the inside of the building, like through fume hoods or paint hoods, things like that. And if you have an industrial ventilation environment like that, then the air that you withdraw from the interior of the building is going to have to be replaced by an equal quantity of outside air, and that outside air that you bring in during the heating season is going to be cold and is going to have to be heated up, and that increases the heating load on your HVAC system. The additional information and guidance in this area is available from publications of the American Society of Heating, Refrigerating, and Air Conditioning Engineers, ASHRAE, which is the leading source of technical information in the HVAC area. The total heating load then is the sum of the transmission loads together with the infiltration and ventilation loads. To this computed total heat load may be added safety factors for things like what is sometimes called pickup or morning warm-up. This is a recognition of the fact that if you have a building with people coming to work from 8 to 5, when they walk into the building at 8 o'clock in the morning, you will have typically, for energy conservation reasons, turned the heating system off at night. And so at 8 o'clock in the morning, the building is cold, and it takes a while for the building to be warmed up so that the occupants are comfortable. And since you don't want the occupants to be in the building shivering for an hour or two before the building warms up, what you might do is turn the heating system on at, say, 7:30 or 7 o'clock and provide some additional heating capacity in your HVAC system to heat the building up quickly and get it up to a nice comfortable condition. And that pickup additional load might be in the vicinity of 10% or something like that of the calculated load due to transmission loss and infiltration and ventilation. Now, with cooling load, the computation of the peak cooling load is a bit different. And this is calculated during of course, during the cooling season, which is the summer. And the considerations in calculating the cooling load first are the transmission and glass solar gain. You have heat transmission through glass, just like you have heat transmission through a wall or through a roof. But you also have solar heat gain, which is the heating by virtue of the electromagnetic radiation that is emitted by the sun. And this is the same physical phenomena as heating something in your microwave oven in your kitchen. Yeah, and I think you've all experienced this when you are outside, say on a sunny day, and you are in the direct sunlight, you are hot. But when you walk over into the shade of a tree or an awning or something like that, immediately you are cooler. And that's because something opaque has been inserted between the sun and you, and the electromagnetic radiation does not pass through opaque objects. There has to be a clear straight line path between the sun and a human being or anything else in order to have heating by the solar heat gain. And so with windows in a building, there is both transmission cooling load and there is cooling load due to the solar heat gain by virtue of the electromagnetic radiation from the sun passing through the glass and heating people who are inside the building. For the cooling load calculation, equation 2.3 is used, which is similar to the one that was used to calculate the transmission load for the heating season. Q is equal to U times A times TO minus TI. T is the outdoor design temperature. That might be 100 degrees Fahrenheit. Indoor temperature, comfortable design temperature, is around 72 degrees Fahrenheit. U is a heat transmission factor, which is something that you just look up in a book for the glazing system that you have, or the wall construction or the ceiling construction that you have. And A is the area of the surface that you are calculating. The glass transmission and solar gain, heat gain due to transmission, first for the transmission of heat through the glass, it's calculated using equation 2.4, which is the same as equation 2.3. Q is equal to U times A times TO minus TI, with U now being the heat transmission factor for the glazing or glass that you are using. The solar heat gain through the windows is calculated using equation 2.5. Q is equal to A times SC times something called SHGF, or solar heat gain factor. The solar heat gain factor, again, is something that you just look up in a book like the ASHRAE guides, or there are other sources for this factor. And this solar heat gain factor varies depending upon the exposure of the windows, north, south, east, west, and also the time of day and the day of the year. And solar SC is something that originally was called a shading coefficient to reflect if the building windows were shaded at the design day and time, but today it's more of an all-encompassing factor that takes into account not only shading by virtue of things like drapes and overhangs and blinds and this sort of thing, but it also is a factor that compensates for the different glazing systems that are now on the market with colored glass and reflective surfaces and things like that. In doing the cooling load calculation, you also take into account the cooling load due to infiltration and ventilation. Again, infiltration is outside air that gets into the building inadvertently, and ventilation is outside air that you bring into the building intentionally for air quality purposes, to prevent the air from getting smelly and unhealthful and causing mold to grow and things like that. The and of course, in the cooling season during the summer, that outside air that you are bringing into the building is hot and has to be cooled down. So that's additional load that is part of your cooling load, and your equipment has to have enough capacity to cool that air down, as well as the cooling load due to transmission and solar heat gain through the glazing. Equation 2.6 is the equation for calculating the heat gain due to infiltration and ventilation, 1.10 times the CFM, cubic feet per minute of infiltration air plus ventilation air, and the TO outdoor temperature, say 100 degrees Fahrenheit, TI indoor design temperature, say 72 degrees. Equation 27 would be used to calculate the cooling load due to latent heat of the air, and we're going to ignore that because that gets into an area called psychrometrics, and which is beyond what we can deal with today. Essentially, what the situation is with latent heating or cooling load is that it's an indication of the quantity of water vapor that is in the air. And in a humid climate, it is often necessary to subcool the air that is going through the HVAC system below the temperature that it would be needed if there were not a high humidity level, and it's cooled below that temperature in order to condense out some of the water vapor that is in the air and reduce the humidity of the air that is in the occupied spaces in the building. And that's because if the air on the inside of the building is humid, it will be uncomfortable and undesirable. Now, infiltration rates, that's the air that comes into the building inadvertently. It comes in through cracks around windows, through cracks around doors, through the fact that doors, people are coming and going perhaps through the exterior doors, and every time they open the door, some of that outside air gets in. And there are some guidelines that are available in the literature for estimating the amount of infiltration, and they typically are based on so many CFM per linear foot of perimeter of the windows, say so many CFM per linear foot of the perimeter of doors, plus perhaps a factor to accommodate the fact that people are opening and closing the doors. Also, the ventilation rates, the air that you bring into the interior intentionally for air quality purposes. There are guidelines for that quantity. This slide here indicates some values that came probably from ASHRAE Standard 62, which is kind of the guideline publication in this area. So you see that in like a bedroom, you would allow for 30 CFM per room for ventilation air to be brought in from the outside. For dining areas, 20 CFM per person, offices, 20 CFM per person, corridors 0.1 CFM per square foot, and so on and so forth. And so you would calculate the ventilation air that you need to bring into the building using these kind of guidelines. There are some correction factors that we're going to skip over because we don't have time to get into this in this presentation, but they are discussed on this slide, and you may want to review them when you have some time. In doing the calculations of the cooling load, in addition to the loads that we have already discussed, the cooling load due to transmission through the walls and the ceiling and through the glass, and the ventilation cooling load due to the outside air you intentionally bring into the building for air quality purposes, and the infiltration load, which is the air that gets into the building inadvertently. In addition to those loads, you also have internal loads that you need to take into account on when doing the cooling load calculation. You ignore these internal loads when doing the heating load calculation because essentially they amount to a safety factor uh, in the heating season. So you just accept these safety factors, and they help to heat your building in the winter, but you have to compensate for them in the summer when you're cooling the building. One of these internal loads that is significant is people loads. A person, their body is at 98.5 degrees, and the design temperature of the occupied space in the building in the summer is, say, 72 degrees Fahrenheit. And so that hot human body is heating up the interior of the building. And how much is it heating it up? Here are some rule of thumb figures. In an office environment, office workers would be providing about 245 BTUs per hour of heating. That second figure that you see there is latent heating, but we're ignoring that in this discussion. You get an environment where the people are more active, like in a factory or something like that, then each person might be heating the interior of the building at the rate of about 345 BTUs per hour. And then you get up to something like a gymnasium with active exercising and so on and so forth. And then a single person might be heating the interior of the building at the rate of about 635 BTUs per hour. The second major source of internal load that needs to be taken into account in calculating the cooling load for a building is that due to lights and also equipment. Lighting in buildings is a significant source of internal heating. The equation that is used there is to calculate that cooling load due to the heat of the lights in the building is Q is equal to 3.41 times the wattage times a factor called the use factor, and then something F sub SA called a special allowance factor. Now this formula as it was originally created is was for calculation where the internal load lighting was primarily incandescent. Now, of course, for energy conservation purposes, we use fluorescent lighting, and we're now even moving to even more efficient forms of lighting, LED lighting lamps. And this F sub SA is a factor that reduces the heating load imposed by the lighting, the cooling load imposed by the lighting, to reflect the more efficient light lamps that are in use today. F sub U is a use factor to take into account the fact that the lights in a given room may not typically be on 100% of the time. They might only be on 50% of the time, and therefore you can reduce the cooling load calculation accordingly. Equipment, if there's significant equipment and office appliances and things like that in a space, they also are a source of heat, which is a load on the cooling system for your building in the summer. And the calculations for that cooling load as a result of motors in the conditioned space is equation 211. And also it should be mentioned that computers, personal computers, are a significant source of internal heat load as well. And the formula for calculation of the cooling load due to appliances and equipment, coffee machines, copiers, things like that, is equation 212. And there are other miscellaneous sources of heat gain, which must be compensated for by the cooling capacity of your HVAC equipment. Another consideration also is that the duct system that is distributing the air around the building uh, leaks, and a duct systems are typically fabricated of galvanized steel, sometimes fiberglass, and there are some other systems that are used for the ducts, but they all leak. A well-constructed and designed system might leak initially around 3%, and so that cool air or hot air, as the case may be, is just lost and has to be compensated for by additional cool air produced by the HVAC system. A poorly designed and constructed system might leak about 10%. Okay, that was a very quick look at the heating and cooling uh, capacity calculations that you need to do to determine the capacity that your HVAC system has to have to heat the air and cool the air. With the for the heating capacity, the mechanisms of heat transmission are transmission through the walls and the ceiling or the roof structure, and then also the heating load due to infiltration and ventilation. You have the same heat transmission when calculating the mechanisms, when calculating the cooling load, but in addition you also have the cooling load due to solar heat gain through windows, and you have the internal uh, loads from primarily people and lights, and if there's a lot of equipment and appliances and things like that in the space, those also contribute to heating the interior of the building, and that heating load has to be compensated for by your cooling equipment. Now we'll move on to chapter 3 here, if you will, and talk about the air conditioning equipment and systems. There are many different pieces of equipment that can be employed in an HVAC system, and different ways of incorporating those pieces of equipment into a system. And what I'll be talking about here is just a representative type of system or systems to give you a feel for what's involved as far as the actual equipment and systems are concerned. First, the cooling systems. What pieces of equipment do you have to make up a system that will produce cool air that will keep the interior of your building cool? Well, back in the old days, if you will, back in the 1900s, the only way of cooling a building or any other space was ice. And actually that was, as you can envision, was so uh, Neolithic that there was no such thing as air conditioning cooling for buildings. In the early part of the 20th century, however, the refrigeration cycle was developed and perfected, and this refrigeration cycle is the basis for all HVAC systems. It's what creates the the cold, if you will, that cools the air inside a building. And it's what you see in this schematic. Now, the original implementation or utilization of the refrigeration cycle was in refrigerators, not in buildings. Um, Subsequently, as the industry matured, the cooling cycle, the refrigeration cycle began to be applied to the cooling of the interior of buildings, and the air conditioning industry was born. And one of the leaders in that was Dr. Willis Carrier, who established the Carrier Air Conditioning Corporation, which is now one of the largest suppliers of air conditioning, manufacturers and suppliers of air conditioning equipment in the US and indeed in the world. So the fundamental elements in the refrigeration cycle are what you see here: a compressor, what is called here is called a condenser, which is a heat exchanger. Heat exchanger is something that allows you to bring something that is hot in proximity to something that is cold. And then there is a law of thermodynamics that says that the hot thing will get cooler and the cool thing will get hotter, and the two media will stabilize at some temperature in between the hot temperature and the cold temperature. And a typical example is a box, you might say, that and running through it is a coil, and you have something that is either hot or cold in the coil, and then air, as an example, is blown through the box, and it comes in proximity with the hot coil, and therefore the air is heated up, or it comes in proximity with a cold coil, and therefore the air is cooled. So the condenser is a heat exchanger. Then there is something called an expansion valve. You might visualize it kind of like the uh, nozzle on your garden hose. And you have water under pressure on one side of the nozzle on your garden hose, and then the water sprays out into the air in fine particles. And part of that air evaporates. The heat of vaporization that is necessary for that evaporation to take place comes from the remainder of the water that is coming out of your hose, and therefore the temperature of the water that is sprayed out of your hose is a little bit cooler than the water upstream of the expansion valve. Then you have another heat exchanger called an evaporator, and you have the piping connecting the evaporator, compressor, condenser, and the expansion valve. And what is in the piping is something called a refrigerant, which is a special material that it was discovered would work well in a refrigeration cycle like this. You couldn't use something like water circulating in this refrigeration cycle, because water doesn't have the proper thermodynamic characteristics. But something that does have the right thermodynamic characteristics, the one that was discovered first, was ammonia. So the first refrigerant was ammonia. And so you have ammonia circulating in the piping, and we'll start in the upper left hand corner, and you have the ammonia, the refrigerant, in the vapor stage, and it is drawn into the compressor, where it is compressed and it gets hot. And you'll recall that hopefully from your Physics 1 course. When you compress something, it gets hot because you're pushing the molecules together, and they are bouncing off each other, and that creates a higher state of thermal energy. So the colder or cooler uh, refrigerant vapor is drawn into the compressor. It is compressed and it gets real hot. And then it is pushed out of the compressor to the condenser. And so you have hot refrigerant vapor in the piping inside the condenser. Now the condenser uh, blowing through it, and it's not shown here, but typically there is a fan that is used to blow outside air across the condenser coil, and that cools the hot refrigerant vapor and it condenses it into a liquid. Now, the outside air in an air conditioning system, the outside air is what we would think of as hot, 100 degrees, but that's still cool compared to the temperature of the refrigerant vapor that has come out of the compressor. So the thermodynamic properties of the refrigerant ammonia, as we're talking about it, is condensed into a liquid. And then the liquid comes out of the condenser, and that's like the water in the hose upstream of your nozzle on your garden hose. And that hot refrigerant is pushed, liquid is pushed through the expansion valve. It is sprayed out, and some of it evaporates, vaporizes, and in the heat of vaporization required to accomplish that results in a combination of liquid and vapor coming out of the expansion valve, just like the nozzle on your garden hose. What comes out, you might say, of the nozzle is a combination of liquid and vapor. And this liquid and vapor is cold. And this cold refrigerant liquid vapor combination is pushed into the evaporator coil, which is a heat exchanger. The return air from the conditioned space in the building, which is kind of warm. It's a little warmer than uh, comfort conditions would want it to be. And that warm air is blown across this cold coil in the evaporator. That cools the air, and then that cold air is pushed by the fan through the duct system to the various occupied spaces in the building, and it cools the people off. And in the process of cooling them, it it heats up. That warmer air then is drawn back into a return duct or return plenum system, and that warmer air, return air, is returned to the evaporator, where it is again blown across the cold coil. So you have, and then the refrigerant, when it comes out of the evaporator, it is in the vapor stage, and then the cycle just continues to rotate like that, from vapor, refrigerant vapor, cooler refrigerant vapor, compressed in the compressor, gets hot, is pushed into the condenser, is cooled by outside air, and condenses into liquid refrigerant, which is pushed through the expansion valve, which causes it to come out of the expansion valve in a combined liquid and vapor state that is cold, and that is pushed into the evaporator coil. The warm return air from the conditioned space is pushed across the cold refrigerant coil, and that cools the air and warms up the refrigerant so that it's now all vapor. Now as I said, the first refrigerant was ammonia. Uh, Ammonia is was quickly learned is a hazardous substance, and so it needed to be replaced, and it has been replaced by some refrigerants that, generally speaking, are some sort of a combination of fluorine, chlorine, and carbon, fluorochlorocarbons. And so that's what contemporary refrigerants basically are. And so that is now used both in refrigerators to cool refrigerators and for cooling of the occupied spaces of buildings. So this is what makes the air cool in order to cool the interior of buildings. Now, we just finished talking about the refrigerant cycle. That's what is needed to cool the air. But you also want to heat the air during the winter when it's cold outside. Typically, the or the way that air is heated again is through a heat exchanger, which can be like a box, and you can have an external flame that is heating the box and making it hot, and then you would have you know, an internal structure, fins and things like that, to control and slow down the passage of air. And you would blow colder air through this box that is hot. And in the process of passing through this box, which is a heat exchanger, the the cold return air from the occupied space in the winter is heated up and is blown by the fan back to the occupied space, where it warms up the room and the occupants, and then that air is drawn by the fan pressures back to the HVAC equipment, and again is pushed through this furnace, and where the air is heated up again, and that circulation just continues. Now the element that heats the air when heating is required in the winter is typically a furnace, or it could be a heating coil, where you would have a hot liquid or steam. The typical heating media are hot water or steam, and so either hot water or steam is pumped into a heat exchanger, and the cold return air from the occupied space is pushed through the heat exchanger and is heated up by the heating coil. So the device that heats the air in the winter when you want heating is typically either a furnace or a heating coil. And this figure here represents the combination of these two tasks, cooling and heating, in one system. And this is what you would call an HVAC system: heating, ventilating, and cooling system. And so you have the refrigerant cycle. It's drawn a little differently here, but it's the same as the one we looked at on the previous slide. And then and that's what operates when you want to cool the air in the summer. But in the winter, you add this second element of a furnace or heating coil that heats the air in the winter when you want to warm up the air. So that's the the fundamentals, if you will, of an HVAC system. You have the refrigeration cycle with the compressor, condenser coil, expansion valve, and evaporator coil, and that's what cools the air. And then for heating, you have a furnace or a heating coil of some sort. Now, and then for the heating system, you would have the furnace or the heating coil. Now let's look at systems, HVAC systems, and how they're kind of categorized. Well, first there's a category you might call central air conditioning systems. And these are systems for applications where several spaces with uniform loads are served by a single apparatus. And they are large systems. They typically over 100 tons of cooling capacity. Now, the term ton of cooling capacity, that's not how much the air conditioning system weighs. The unit of heat transfer is the British thermal unit, and back in the 1890s, it was ascertained that it takes 12,000 BTUs to melt 1 ton of ice. And so the term 1 ton of cooling capacity came into use, and it continues to be the standard terminology that's used in the industry these days. 12,000 BTUs, or British thermal units per hour, as far as cooling capacity is concerned. That's called a 1 ton air conditioning cooling unit. If it was 60,000 BTUs per hour cooling capacity, that would be a 5 ton cooling HVAC system, cooling capacity HVAC system. And central air conditioning systems are typically large systems over 100 tons capacity. Now, there are a number of different ways that a central air conditioning system can be put together, bringing together various pieces of equipment and connecting them up and constituting a central air conditioning system. This is just one way of doing it. It's a common way. This is a system that you would find perhaps in, say, a mid-size office building or building and a multi-story building is represented here. And you see down at the bottom there, this would be in a mechanical room in the building. You have something that creates the cold and something that creates the hot. And the thing that creates the cold is called a chiller, and that contains all of the elements of the refrigeration cycle. But instead of it cooling air directly, it cools water. And so the refrigeration cycle and the refrigerant is all within that piece of equipment called a chiller. So there's the compressor, there's a condenser coil, there's an expansion valve, there's an evaporator coil, but instead of air being blown through the evaporator coil and being cooled, it is water that is pumped through. And so what comes out of the chiller is chilled water. It's cold, and there are chilled water pumps that pump that water. Now also down in the basement or in the mechanical room is another piece of equipment called a boiler. And the boiler is either a hot water boiler or a steam boiler. And steam is certainly a common heating media, but in the typical commercial applications that we see, steam is not used that much because it's kind of high maintenance. So you've got in the basement or in the mechanical room, you've got a machine called a chiller that is producing cold water. And you have and all of the refrigerant cycle items are in that chiller. And then you have a boiler which is creating hot water, and the boiler is just a big tank that you have a burner that is heating it up, and it's heating the water in the boiler. And then you have pumps that pump the hot water and pump the chilled water. And what they do is they pump it to, in this illustration, a fan room on each floor of this building. And the fan room on each floor of this building is a room. And in it is a piece of equipment called an air handler, which is a box of special configuration that contains a fan and a hot water coil and a chilled water coil. And the fan pushes the air through the coils, either the hot water coil or the chilled water coil. And you do not have you're not utilizing the hot water coil in the summer because you don't want to heat the building, and in the winter you do not want to operate use the chilled water coil. So in the winter you have hot water being created at the boiler, and it is pumped through the coil, hot water coil in the air handler, and the return air from the room is pushed by the fan through that hot coil. It heats up that air and pushes it to the occupied spaces where it is through a ductwork system, and then it is discharged into the occupied space, and it heats up the occupied space. And then the return air would be returned. It could be in one configuration returned in a return air duct, or in the illustration here, this system is using the plenum space, what's called the plenum space, which is the space between the drop down ceiling, suspended ceiling in the office space, we'll say, and the floor deck above. And the return air is pushed in after it has heated the occupied space. It is drawn by the fan pressure up into the plenum space, and then there is you see a little piece of inverted L-shaped ductwork that is sucking the air out of the plenum and into the fan room, and then the air in the fan room is sucked into the air handler, and then it is pushed through the hot water coil, and it is heated up, and it returns to the occupied space, warms up the occupied space, and the air cycle just continues like that. And it does this on each floor. You also see some ductwork there that it's not terribly well drawn in this illustration, but what that ductwork is doing is when the return air is returned to the fan room, a certain percentage of it, say 15 to 25%, is forced by fan pressure outside through an exhaust duct and is exhausted to the outside of the building. And then that air is replaced by drawing in outside air, which mixes with the remaining, say, 85% of the return air. And that combination of return air plus outside air is what gets pushed through the hot water coil and is heated up, and the fan pushes it through the supply duct system to the occupied space, and the cycle continues. And then during the summer, when cooling is needed, the boiler is turned off, the hot water pumps are turned off, hot water is no longer circulating, chilled water, cold chilled water is circulating. And so the chilled water is pushed by the chilled water pumps to the air handlers on each floor and into the chilled water coil. The return air from the occupied space is pushed through the chilled water coil and is cooled and pushed by the fan to the occupied space and where it cools the occupants. Then the fan pressure pushes the slightly warmer air out of the occupied space and to the either into the return air plenum or to a return duct system, and it is returned to the air handler, where a portion of it is exhausted to the outside, and the portion exhausted is replaced by an equivalent quantity of outside air that is brought in, and that's your ventilation air coming in. And then that combination of return air plus outside air is what is pushed through the chilled water coil, and that is how you are heating and cooling the different floors of this building. Now, you also see a piece of equipment up at the top there labeled a cooling tower. Now, you recall in the basic refrigeration cycle the condenser coil, and in the illustration we looked at, the condenser coil was what you would call an air-cooled condenser. In other words, the refrigerant, the hot refrigerant is pushed into the coil in the condenser, and it is cooled by outside air being blown across the hot refrigerant coil. But you could also, instead of cooling the refrigerant coil using outside air, you could also use cool water or cooling water. And using cooling water for thermodynamic reasons that we can't go into is more efficient and is typically used in larger air conditioning systems like these central systems we're talking about here. In other words, you would not use an air-cooled condenser, but you would use a water-cooled condenser. And the water for cooling the condenser comes from the cooling tower. And here is a schematic that kind of illustrates that. Now, this is a little bit different representation of what would be going on. You see the evaporator, and in the previous illustrations we've talked about, it is return air that is blown across the evaporator and is cooled by the cold refrigerant in the coil. But you can also, instead of cooling the air directly, you can cool water, and that's what you are cooling with this system that you see here. So instead of return air passing through the evaporator, in this system you are pumping water through the evaporator, and in the evaporator the water comes into contact with the cold refrigerant coil, and the water is cooled, and so chilled water comes out of the evaporator, and it is pumped in pipes around the occupied spaces, and throughout the occupied spaces are a series of what in essence are small air handlers that contain a fan and a chilled water coil. And this chilled water is pushed by the pump into the fan coil units. The fan coil, the fan in each one of these fan coil units blows the air from the occupied space across the chilled water coil, and it cools the air. And then that will warm up the chilled water somewhat, and the pump pressure pushes that chilled water back to the evaporator, where it is cooled down again. And you see in this illustration, it's indicating that the return chilled water to the evaporator is at 10 degrees centigrade. It's cooled down to around 6 degrees centigrade when it comes out of the evaporator, and it's that 6 degree centigrade water that is pushed by the pumps to the fan coil units, and then the air from the occupied space is blown across that chilled water coil to cool the air in the occupied space. So that's kind of the circulation loop there at the bottom in this illustration. It is a chilled water circulation. In the center there is the is the refrigeration cycle, with the refrigerant in the pipe and containing all of the fundamental elements: the condenser, the compressor, the evaporator, the expansion valve. What is different here, though, is that in a larger system like this, instead of using an air-cooled condenser and blowing outside air across the condenser coil to cool the hot refrigerant when it comes out of the compressor, cooling water is used. And so you have a cooling water cycle represented by the piping up at the top of this schematic, and there you see this piece of equipment called a cooling tower, and water circulates in this cooling water cycle. The cooling tower consists of a basin at the bottom that holds water, and water is drawn out of it by a pump, and it is pumped to the condenser coil, where it cools using the water, which is at around, in this illustration, say 25 degrees centigrade, and that water is pushed across the condenser coil, and it cools the refrigerant so that the refrigerant condenses. And in the process of cooling the refrigerant, it is heated up. That cooling water is heated up to, say, in this illustration, 30 degrees centigrade. That water is pumped back to the cooling tower, to the top of the cooling tower, where it is sprayed out of nozzles in the top of the cooling tower. Some of that water evaporates as it is sprayed out of the nozzles and falls down through the cooling tower. And the heat of vaporization to vaporize that quantity of the cooling water needs to come from the cooling water itself, and therefore the cooling water is cooled as it falls from the nozzles at the top down to the basin at the bottom, so that you have 30 degrees centigrade water being returned to the cooling tower. It is sprayed out of nozzles at the top, falls down to the bottom, and in that evaporative cooling process it is cooled down to 25 degrees centigrade, and that cooling water just continues to circulate. Now, with a cooling tower, since the some of the water is being vaporized and gets blown away, you have to have makeup water, and that amounts to maybe 1 to 1.5% of the water that vaporizes. So this is a picture of a common central air conditioning system. The fundamental refrigeration cycle is right there in the center with refrigerant in the piping, but the evaporator coil, instead of cooling the air directly, it is cooling water, which is therefore chilled, and is pumped to small air handlers called fan coil units that are located throughout the building. And then the air from the occupied spaces is blown by a fan in the fan coil unit across the chilled water coil and is cooled by that chilled water coil. And then up at the top, instead of having an air-cooled condenser, you have a water-cooled condenser, and you are using a cooling tower. So this is a pretty typical system. This is another picture of a cooling tower for a water-cooled condenser. Just the cooling tower itself. You see down at the bottom is the tank or basin into which the water, cooling water, falls. It is pumped out, pumped through the condenser heat exchanger, here just called a heat exchanger. In the process of passing through the condenser, it is heated, it is warmed up, and that warmer water then is pushed by the pumps to the top of the cooling tower, where it is sprayed out of nozzles. It falls down through the cooling tower, and in the evaporative cooling process, its temperature is lowered, and it falls back down to the bottom into the basin, and the cycle continues. And then you have to have makeup water to compensate for that percentage of the cooling water that gets vaporized and blows off into the atmosphere and gets lost. This is another representation of the same thing, a cooling tower on the left, and then you see the condenser, which is cooling the refrigerant, and you see the refrigerant piping there. And so that is another illustration of this system. Here are some photographs of cooling towers so you can get a feel. These are not small pieces of equipment, and so you don't use them on small systems. You used air-cooled condensers rather than water-cooled condensers. And these are also high maintenance items, so it's just not economical to use a water-cooled condenser on a small air conditioning system. Now this is a great big huge cooling tower, and very high capacity for generating cooling water, and this kind of a cooling tower is found only at very high capacity locations like nuclear power plants and this sort of thing. And the stereotypical configuration there is that way because it causes naturally induced air drafts to facilitate the cooling of the watt of the cooling water. So the air is drawn in at the bottom of the cooling tower and it rises and is exhausted through the top. And that air draft mingles with the water as it is being sprayed, and as the water is falling down to the bottom, the air is moving upward, and this facilitates the mingling and the of the air and the water and the heat. The next category of air conditioning systems is unitary air conditioning systems. These should generally be limited to loads less than 100 tons. Unitary systems are packaged in self-contained or split configurations. Self-contained units incorporate components for cooling or cooling and heating in one apparatus. Thermostatic expansion valves are preferred over capillary tubes and orifices for refrigerant control when available as a manufacturer's option, since expansion valves provide better superheat control over a wide range of operating conditions. Split systems may include the following configurations: direct expansion coil and supply fan combined with a remote compressor and condenser coil, or B, direct expansion coil, supply fan and compressor combined with a remote condenser cooling tower or ground loop system. These systems generally have lower first costs than central systems but may have higher life cycle costs. If part load operation is anticipated for a majority of equipment operating life, they consider multiple unitary equipment for superior operating efficiencies and applied reliability. Refer to the ASHRAE Handbook Equipment for size and selection criteria. This illustration is of a typical unitary air conditioning system providing cooling only. All of the fundamental elements of the refrigeration cycle are in this one package. This is a photo of a typical unit which you will most likely recognize, being very commonly used in residential and small to mid-size commercial installations. Another photo of a unit. This is an illustration of a split system air conditioning with cooling only. On the left-hand side is the outside unit, which on the left side is the indoor unit, which is a box inside the building containing the fan and the refrigerant coil or the evaporator coil. And on the right is the outside unit, the outdoor unit, containing the compressor and the condenser heat exchanger. This is another picture of a split system. This one includes a furnace in the indoor unit to provide heating, and so in the indoor unit you have the fan moving the air about the occupied space, the evaporator cooling coil, and on the outside the unit consists of the condenser coil, fan, and compressor. A third category that is just essentially a small unitary unit are room air conditioning units. These units are self-contained and serving only one space. They're typically referred to as window or through-the-wall type air conditioners. Rooms served by these units should have a separate HVAC unit to provide ventilation air for a group of rooms. Use them when they are life cycle cost effective, and refer to the ASHRAE Equipment Handbook for further information. Another category of units is built-up systems. These consist of individual components assembled at the building site, and they are generally used where large or unusual air conditioning requirements exist, such as industrial processes and so on. These systems may be used as remote air handling systems with a central cooling plant, unitary air handling units. Determine the number of air handling units by an economic division of the load, considering the value of space occupied by equipment, the extent of ductwork and piping, the multiplicity of control, maintenance, and operating points, and energy conservation factors. Heating sources can be either steam, hot water, natural gas, oil, electricity, or some sort of renewable resource. Select these sources based on life cycle cost. Heating systems may be combined with ventilating systems when feasible. Heating-dominated climates require perimeter radiation at windows in office spaces. Locate individual heating plants in the building they serve or in a separate adjoining building. For central heating plants, base the total heating system capacity on normal demand rather than total connected load. With regard to all air systems, refer to the ASHRAE Systems Handbook. In humid climates, provide all air systems for air conditioning. These systems are central systems which provide complete, sensible, and latent heating and cooling of the air supply. These systems are either single path or dual path. Single path systems have heating and cooling elements in a series configuration. Dual path system elements are arranged in parallel. Consolidation of system components at a central location provides increased opportunity for energy conservation. One category of air system is the constant volume system, used where room conditions are to be maintained by supplying a constant volume of air to the space and varying supply air temperature in response to demands for net space heating or cooling. In addition to multi-zone systems, this includes single-zone or single-space applications for spaces such as auditoriums, meeting rooms, cafeterias, restaurants, and small retail stores. Multi-zone systems use these systems to provide individual temperature control of a number of small zones, maximum of 10 zones from a central air handler. For normal comfort cooling applications, place heating and cooling coils in the air handler. For applications where humidity control is critical, place coils in series so that the air is conditioned by the cooling coil prior to passing to the hot deck. Provide cooling by direct expansion or chilled water coils. Provide heating by steam coils, hot water coils, or electric coils. Another category of units is the terminal reheat systems. These systems overcome zoning limitations by adding individual heating coils in each zone's branch duct to compensate for areas of unequal heating load. Heat, whether in the form of hot water, steam, or electrical resistance heaters, is applied to either preconditioned primary air or recirculated room air. These systems waste energy because supply air is cooled to a low enough temperature to serve the zone needing the coolest air, but then supply air must be reheated for other zones to avoid overcooling. Where constant volume is maintained, the waste of energy can be even more significant. Reset cold deck temperature to meet cooling requirements of the room with the largest load or to satisfy humidity requirements. This cold deck temperature control reduces energy consumption. Due to high energy consumption, limit these systems to applications requiring close control of temperature and humidity, such as hospital intensive care areas and laboratories. When economically feasible, use heat recovered from the refrigeration cycle in heating coils. Another category of air systems is variable air volume systems. Use variable air volume systems, VAV systems, for buildings with sufficient zones, typically 11 or more zones, and load variation to permit reduction of fan capacity for significant periods during the day. Do not use bypass VAV systems. The complexity of systems should be consistent with minimum requirements to adequately maintain space conditions. An important consideration in air systems is the economizer cycle. The economizer cycle should not be used in humid climates and for spaces where humidity control is critical, such as computer rooms. Problems have been experienced with linkage corrosion, excessive damper linkage, jammed linkage on large dampers, and inadequate maintenance. Outdoor air dampers should be located away from the intake louver and after duct transition to minimize exposure to weather and size of dampers. Provide outdoor air dry bulb changeover rather than enthalpy or outdoor air return air comparator changeover. With VAV systems, return or relief fans should not be used. An economizer should only be used when it can be designed with gravity relief through the building envelope. Size gravity relief dampers to prevent building overpressurization. For size and selection criteria of systems and equipment, refer to ASHRAE Equipment Handbook. HVAC systems shall be able to dehumidify supply air under loading conditions, provide reliable operations, and tolerate reasonable variations in chilled water temperatures. Air conditioning systems generally operate at part load conditions most of the time. This is particularly true of comfort air conditioning systems, which often operate at less than 50% of their design load capacity for more than 50% of the time. Since high part load efficiencies are desirable to conserve energy, the selection of equipment and step starting and sequencing controls shall be made with emphasis on reducing life cycle costs at part load conditions. Verify and document the equipment operation in accordance with ASHRAE Guide Number 1, Commissioning of HVAC Systems. Now we move to Chapter 4, Air Distribution. Duct design for HVAC systems, the sizing in general. Refer to the ASHRAE Handbook Fundamentals, which recognizes three methods of sizing ductwork: the equal friction method, the static regain method, and the T method. The ASHRAE Handbook also provides a commonly used chart for sizing ducts using the equal friction method. For design of small, simple systems, the equal friction method will suffice. Use the static regain method for variable air volume. The equal friction method sizing. Select a constant pressure loss in inches of water per 100-foot length of duct from the preferred part of the ASHRAE equal friction sizing chart. The preferred part is between 0.08 and 0.6 inches of water per 100 feet friction loss for air quantities up to 18,000 CFM and between 1,800 feet per minute and 4,000 feet per minute for air quantities greater than 18,000 CFM. Use low velocities and a low friction drop for small projects or where ductwork is cheap and energy is expensive. For systems of 18,000 CFM and over, use a friction loss of 0.08 and velocities of 1,800 to 3,000 feet per minute. After sizing the entire system at the selected unit pressure drop, go back and adjust velocities and pressure drops in the shorter branches to equalize the pressure drops at each duct branch junction. With regard to ductwork in general, round ducts should be used wherever possible. Under normal applications, the minimum duct size should be 4 inches in diameter. Use smooth curved elbows as much as possible. If these are not available, use 3-piece elbows for velocities below 1,600 feet per minute and 5-piece elbows for velocities above 1,600 feet per minute. The throat radius shall not be less than 0.75 times the duct diameter. With regard to rectangular ducts, use a minimum duct size of 6 inches by 6 inches. Where possible, keep one dimension constant in transitions and do not make transitions in elbows. Make transitions in sides and bottom of the duct, keeping top level to maintain maximum clearance above the ceiling. Duct sizing calculators are available. This is an illustration of one that's available from the Train company. The transition slope should be 30 degrees on the downstream. Where ductwork is connected to equipment fittings such as coils, furnaces, or filters, the transition shall be as smooth as possible. Drawings shall indicate ductwork pitch, low spots, and means of disposing of the condensate. Elbows shall be smooth with an inside radius of 1.0 times the width of the duct. Where space constraints dictate use of mitered elbows, use elbows that shall have a single thickness turning vane. Using double thickness turning vanes instead of single thickness vanes increases the pressure loss of elbows by as much as 300%. Use the circular equivalence table in ASHRAE Handbook Fundamentals instead of matching areas when you change aspect ratios. The aspect ratio is the ratio of the larger to the smaller rectangular duct dimension. Try to use an aspect ratio of 3:1 with a maximum aspect ratio of 6:1 or less. Show access doors or panels in ductwork for apparatus and devices for maintenance, inspection, and servicing. To save construction expense, flexible duct may be used to connect ceiling outlets. Limit the length of flexible ducts to straight runs of 5 feet. Seek self-balancing by having equal lengths of flexible ducts instead of long and short lengths on the same branch. Do not use flexible ducts for elbows, including connection to diffusers. Provide elbows at ceiling diffusers. Do not use flexible ducts in industrial ventilation systems. Rooftop ducts exposed to the weather can leak rainwater. Exterior insulation tends to have a short life. One way to avoid such problems is to put the insulation inside the duct and then use galvanized steel ductwork with soldered joints and seams. Exterior insulation shall have weatherized coating and wrapping throughout and where it must be used, such as on kitchen exhaust hoods containing grease. Glass fiber ductwork is an option. Investigate the building climate in your local area before deciding that ductwork made from glass fiber panels will always be less expensive than galvanized steel ductwork. Fiberglass ductwork should be coated inside to avoid bacteria growth. In some parts of the country, the sheet metal subcontractor may make or buy metal ducts made on an automatic machine at competitive prices. Provide balancing dampers on duct branches and show dampers on drawings. Use extractors or volume dampers instead of splitter dampers at branch connections. Do not use splitter dampers since they make ductwork more difficult to balance than a job with volume dampers. Provide access in the ceiling and clamping quadrants for dampers or use a type with a remote control that extends through the ceiling. Outdoor air dampers should be located away from the intake louver and after the duct transition to minimize exposure to weather and oversizing of dampers. Avoid using balancing dampers for industrial ventilation systems. Design industrial ventilation ductwork so that the system will function properly without balancing dampers. Do not use balancing dampers when designing a VAV, variable air volume system. A VAV system with ductwork designed using the static regain method and properly sized VAV terminal units is inherently self-balancing. Fire dampers and smoke dampers are important in the air distribution system. The term fire damper usually means a curtain-type damper which is released by a fusible link and closes by gravity or a mechanical spring. Fire dampers are mounted in walls of fire-rated construction to ensure integrity of the space. Fire dampers should be installed where the passage of flame through a fire-rated assembly is prohibited. Combination fire and smoke dampers are an option. The term combination fire and smoke damper usually means a fire damper which is automatically controlled by an external source such as a fire alarm control panel or energy management system to stop passage of both fire and smoke. Combination of fire and smoke dampers should be installed where passage of fire or smoke is prohibited. Activation of combination fire and smoke dampers can be by several methods including pneumatic damper operators, electric damper operators, and electrothermal links. Electrothermal links include explosive squibs which are not restorable and McCabe type links which are restorable. Pneumatically operated dampers are the preferred method of damper activation and should be configured in the fail-safe mode such that loss of pneumatic pressure will result in damper's closure. In electronic data processing rooms, combination fire and smoke dampers should be installed in walls with a fire resistance rating of 1 hour or greater. In other type spaces, either fire dampers or combination fire and smoke dampers should be installed in walls with a fire resistance rating of 2 hours or greater. Where a smoke damper is required to stop passage of smoke through a barrier, such as in hospitals, the installation of a combined fire and smoke damper is required. Fire dampers and combination fire and smoke dampers must remain in the wall during a fire. Though ductwork may collapse, the damper should remain in the fire-rated assembly. Therefore, indicate on drawings the details for attaching dampers to the wall. Use Underwriters Laboratories listed fire-stopping materials between the damper collar and the wall, floor, or ceiling assembly where penetrated. Fan system effect factors. Fans are tested and rated based upon a certain standard ductwork arrangement. If installed ductwork creates adverse flow conditions at the fan inlet or fan outlet, loss of fan performance is defined as a system effect factor. The system effect factor can be caused by obstructions or configurations near the fan inlet and outlet. For example, failure to recognize the effect on performance of swirl at the fan inlet will have an adverse effect on system performance. Refer to Air Movement and Control Association, AMCA, Standard 201, Fans and Systems for additional information on fans and system effects. Moving on now to Chapter 5, some simple little rules of thumb. The following information provides guidance that could be used in planning to estimate utility requirements and to assess the adequacy of equipment sizing during design reviews. Note that it is preferable to do a quick block load calculation instead of using these rules of thumb. With regard to air conditioning capacity, see Table 5.1, which you will see shortly. For heating capacity, 35 to 40 BTUs per square foot for mild climate regions, less than 4,000 degree days, and no fresh air load. Chilled water circulation, rule of thumb, 2.5 to 3 gallons per minute per ton. Hot water requirements, gallons per minute, assuming a 20 degree temperature drop, BTUs per hour divided by 10,000. Gallons per minute, BTUs per hour divided by 500 times the temperature drop. With regard to condenser water, required thermal capacity of cooling water equals 15,000 BTUs per hour per ton, or 3 GBM per ton. Steam, assume 1 pound of steam per 1,000 BTUs. Condensate, 120 gallons per 1,000 pounds of steam. Table 5.1 provides some rules of thumb for air conditioning cooling capacity for different space uses. Now we move on to Chapter 6, Heating and Cooling Media Distribution. This discussion provides criteria and guidance for the design and construction of heating and cooling distribution systems outside of buildings. The mediums used in these distribution systems include high temperature hot water, HTHW, 251 to 450 degrees Fahrenheit, low temperature hot water systems, 150 degrees to 250 degrees Fahrenheit, low pressure steam systems under 15 psig, high pressure steam systems over 15 psig. Condensate return systems up to 200 degrees Fahrenheit, and chilled water systems for cooling. The distribution media selection when connecting to an existing system, almost all heating and cooling distribution systems will be connected to an existing central distribution system. In this case, the designer most often designs for the media to which it is being connected. High temperature hot water, low temperature hot water, steam condensate, or chilled water. For installation of a new system, when no existing system is present, the designer must select the system that is most appropriate for the end user. High temperature hot water and steam condensate state systems are the most common types of distribution systems currently used. However, a new system should only use the temperatures and pressures necessary to meet the requirements of the installation. For example, the use of high-pressure steam sterilizers or steam kettles at several facilities may require the use of a high-pressure steam system or high-temperature hot water system. It is usually more cost-effective on a first cost and life cycle cost basis to use a low or medium temperature hot water distribution system whenever possible, and to incorporate standalone high-pressure temperature systems where required. The lower maintenance costs, safer operation, longer life of systems, and simpler system controls for hot water systems often offset the costs of larger piping required. For further information for selecting the system type, refer to the ASHRAE Handbook, HVAC Systems and Equipment. When selecting a distribution system, the designer must determine which system types apply to a particular medium. The designer must also exclude systems which are not appropriate for a particular site or for which the customer has no interest. Examples of this are locating above-ground systems in non-industrial areas where the installation is sensitive to the aesthetic appearance of the area, or routing concrete shallow trench systems through drainage swales or floodplains. With regard to heat distribution systems in concrete trenches, this system is a buried system with its removable concrete cover installed at grade and will typically be used for high temperature hot water and steam condensate systems. In rare instances, it may also be used for chilled water and low temperature hot water in the event no plastic piping is installed in the same trench as high temperature greater than 250 degrees Fahrenheit piping systems. Experience has shown that if insulation of a high temperature system is compromised, temperatures can increase to such a level and cause damage to the plastic piping. Figure 2 is a typical trench and cover dimension detail. Thermal expansion in systems is important and is may be accommodated by expansion loops, such as you see here in figure 6.3. Thermal expansion is required, so the piping must be anchored periodically, and then between anchorage points sliding mounts need to be employed, and these are details for the mountings, and these are details for pipe anchors. Thermal expansion can also be accommodated by expansion couplings, illustrated here in figure 6.7 and in figure 6.8. Another category of media distribution is pre-engineered underground heat distribution systems. This system is designed for higher pressure and temperature applications. The two types of pre-engineered systems are the drainable, dryable, testable, or DDT type, which is used for high pressure steam and condensate and high temperature hot water at many sites, and high temperature hot water at any type of site. And the water spread limiting type, WSL, which is used only for steam condensate systems in bad and moderate sites. High temperature hot water supply and return lines may be provided in a single casing. However, steam and condensate lines must always be provided in separate casings because condensate lines typically last less than half as long as the steam line and are easier to replace when in a separate casing. And this is a simple illustration of casing types for pre-engineered systems where the pipe and with insulation is inside of an exterior casing. Another illustration in which two lines are carried in the same casing. Another category of media distribution systems is prefabricated underground heating and cooling distribution systems, which are designed for lower temperature and pressure applications. They are typically used for LTHW, low temperature hot water, chilled water, or combination low temperature hot water, chilled water systems. These systems have features similar to the other distribution systems described, and it is distinguished by the fact components are largely prefabricated rather than field fabricated. Above ground distribution systems may be used for high temperature hot water, steam condensate, and low temperature hot water systems, and for chilled water systems where freezing is not a concern, although there are the considerations of aesthetics with above ground systems, and also the fact that above ground systems interfere with pedestrian and vehicular circulation. This is an illustration of a typical pre-engineered above ground system. The system type selected needs to be based on the type of media that is distributed. With regard to high temperature water and steam condensate systems, the order of preference for system types for high temperature and high pressure systems is first, above ground heat distribution. This is the least expensive system and historically requires the lowest maintenance and operating costs. However, the safety and aesthetics of an above ground system are not always desirable and must be accepted by the end user. Secondly, heat distribution systems in concrete trenches. This is the most dependable of the buried distribution systems. The piping is totally accessible through removable concrete covers. The piping does not come in contact with the soil, and groundwater is drained away from the piping system to low point drains. Except in rare instances, this is the system that would normally be selected if above ground is not acceptable with the user. And third, pre-engineered underground heat distribution system. This type of buried distribution system should be selected as the last option due to very short system lives, which are typically caused by poor drainage, poor corrosion protection, and improper installation. Instances where it would be used would be when above ground is not acceptable with the end user, or when drainage swales and high groundwater prevent the installation of a concrete trench system. With regard to low temperature and chilled water systems, low temperature hot water and chilled water systems, the order of preference for system types for hot water, chilled water, or combination hot chilled water are first, above ground heat distribution system. This is the least expensive system and historically requires the lowest maintenance and operating costs. However, the aesthetics of an above ground system are not always desirable and must be accepted by the end user. In addition, above ground systems are typically not used for chilled water because of potential freezing problems in colder climates and heat gain in warmer climates. Secondly, prefabricated underground heating cooling distribution systems. This buried distribution system is relatively inexpensive and dependable. The non-metallic casing materials provide excellent protection from corrosion, and the lower temperatures and pressures allow the system to operate for extended periods of time. It is an excellent application for chilled water since the system is installed underground, limiting the amount of heat gain to the system. General system design considerations. Some aspects of a heating or cooling distribution system design are similar regardless of the system type. These aspects are discussed below. First, site soil survey. After general routing has been proposed and before specific design has begun, a detailed soil survey should be conducted for all distribution systems. The survey will be made after the general layout of the system has been determined and will cover the entire length of the proposed system and will be made by a geotechnical engineer. The geotechnical engineer will be a registered professional engineer, typically with a minimum of 3 years of experience in the field of soil mechanics and foundation design. This engineer also must be familiar with local soil conditions. If at all possible, the survey should be conducted during the time of year when the groundwater table is at its highest point. If this is not possible, water table measurements will be corrected on the basis of professional judgment and local knowledge to indicate conditions likely to exist at the time of year when the water table is at its highest point. It may be necessary to dig test pits at the worst locations to investigate the soil for evidence of high water table. As a minimum, information on groundwater conditions, soil types, terrain, and precipitation rates and irrigation practices in the area of the system shall be collected. This information will be obtained from available records. In addition, soil resistivity will be determined for the cathodic protection system design. Information on groundwater conditions and soil types. In most cases, this is not necessary for prefabricated underground heating and cooling distribution systems and above ground heat distribution systems. Will be obtained through borings, test pits, or other suitable exploratory means. Generally, a boring test pit will be made at least every 100 feet along the line of the proposed system within the areas of prior construction. In open, undisturbed natural areas, the spacing of borings may be increased. Each exploratory hole shall be extended to a level at least 5 feet below the anticipated elevation of the bottom of the proposed system. If a significant difference in underground conditions is found at adjacent exploratory points, additional explorations will be made between these points in order to determine more precisely where the change occurs. Upon completion of the survey, each exploration point will be classified on the basis of the criteria presented. The classification criteria are different for each system. Note that although classification is not a requirement for design of prefabricated underground heating and cooling distribution systems or above ground heat distribution systems, the site survey, except for boring or test pits, must be conducted to ensure that actual site conditions have been identified so that accurate plan and profile drawings can be generated. A utility investigation is essential. All existing, concurrently constructed and new utilities need to be identified if within 25 feet of the proposed distribution system routing. If the proposed routing crosses any utilities, burial depths must be determined. Utility locations and depths can be verified through personnel familiar with utilities, utility maps, and by site visits. The designer is responsible for these site visits to verify locations of utility interferences and to coordinate all other construction items with the user. In the event utility information is not available, utility location consultants may be procured who specialize in the location identification and depth determination of utilities. If interference exists, details will be provided in the design to relocate utilities or modify system routing to avoid the interference. All distribution systems require a layout plan and profile, and that must be provided by the designer. Layout plans will include but not be limited to system routing, including expansion loops and bends, manhole locations, and anchor locations, station numbering for the system, one-dimensional coordinates from the point of origin of the distribution system, all utilities within 25 feet of the system, all roads and buildings clearly labeled, types of surface conditions such as asphalt, concrete, seeding, gravel, etc., grade contour lines, both new and existing, and all dimensions and clearances to ensure accurate routing. A profile of the system is to be drawn and as a minimum should show all station numbering, system slope drawn to scale 1 inch to 20 feet minimum for all systems to all points, new and existing grade, all existing or new utilities shown at their actual burial depths. Expansion compensation is essential with heating and cooling media distribution systems. All expansion systems, loops, and bends must be sized in order to prevent excessive pipe stresses due mainly from thermal expansion and from exceeding those allowed by the ASME Power Code ASME B31.1. Mechanical expansion joints are not recommended for absorbing system expansion. Mechanical expansion joints greatly increase the maintenance requirements of the distribution systems. In the unlikely event that expansion joints must be used, they must be placed in an adequately sized valve manhole. The designer is responsible for expansion calculations for heat distribution systems in concrete trenches, prefabricated underground heating cooling distribution systems, and above ground heat distribution systems. The designer is also responsible for the expansion and stress determinations in all the valve manholes, including the location of the equipment pipe support locations. Even though the manufacturer is responsible for the expansion calculations for pre-engineered underground heat distribution systems, the calculations must be thoroughly reviewed by the designer at the shop drawing level. It is recommended that a three-dimensional finite element computer program be used for determining system stresses. Many finite element software packages are available which operate on desktop computers. The temperature differential used in the stress analysis will be the maximum temperature of the media less the medium temperature the system will encounter during a shutdown. All loops and bends must be sized based on 0% cold springing. Cold springing effects lessen over time and are difficult to maintain in the event the system is ever cut, and shall therefore not be included in the analysis. However, loops may be installed with cold springing as an added conservative measure. Valve manholes are an important consideration. For all distribution systems, valve manholes shall be designed by the project designer. A valve manhole is required for all buried systems, lateral connections, all below to above ground system transitions, all drain points, low points, and all below ground valving, all trap stations, high points of vents of buried systems, and to minimize depth of buried systems. Distance between valve manholes varies with different applications. However, spacing shall never exceed 500 feet with pre-engineered underground heat distribution systems or prefabricated underground heating cooling distribution systems to minimize excavation when searching for failures and to minimize effects of a failure. To enhance maintainability, avoid manholes deeper than 6 feet. Layout of each manhole shall be designed on a case-by-case basis. It's important to first lay out to scale all manhole piping, insulation, valving, with stems upright 90 degrees or less from vertical, and equipment, and then locate the manhole walls around these appurtenances to ensure adequate manhole size and room for maintenance personnel. One-line diagrams of piping and equipment are unacceptable. Figure 6.1 is a typical manhole plan. Note that all valve manhole layouts have certain designer requirements in common. The designer will Figure 6.1 is a typical manhole plan. Provide mainline isolation valves in valve manholes to most efficiently minimize outages to buildings served by the distribution system. When installed, mainline isolation valves will be located downstream of the building's service laterals. Provide lateral isolation valves within the valve manholes for all lateral runs. Locate all carrier pipe vents and drains needed within the manhole for proper system drainage of the main and lateral lines. Lay out all valve manhole internals such as valves and valve stems and piping with insulation. Lay out all valve manhole internals to scale to ensure adequate clearance has been provided for operation and maintenance within the manhole. Ensure that no non-metallic piping is routed in the manholes, i.e., as allowed with chilled water or condensate return systems, which also serves high temperature mediums that could damage the non-metallic piping. Damage to non-metallic piping is caused when manholes flood and the hot piping boils the flood water. Boiling water can exceed the temperature allowables of many non-metallic piping systems. Because of this, the designer must transition to steel piping at the manholes. Table 6.1 indicates typical valve hole manhole clearances. Access ladders will be required on all valve manholes greater than 3 feet in depth. Ladders will be welded steel and will consist of uprights and non-slip steps or rungs. Uprights will be not less than 16 inches apart, and steps or rungs will be spaced no greater than 12 inches apart. Ladders will extend not less than 6 inches from the manhole wall and will be firmly anchored to the wall by steel inserts spaced not more than 3 feet apart vertically. All parts of the ladder must be hot dip galvanized after fabrication in conformance with ASTM A123. The top rung of the ladders shall be not more than 6 inches from the top of the manhole. A typical valve manhole access ladder detail is shown in figure 6.2. This is figure 6.2, a typical access ladder. Insulation for valves, fittings, field case enclosures, and other piping system accessories in valve manholes should be of the same types and thicknesses as those provided in the distribution system's guide specification. All insulation shall be pre-molded, pre-cut, or job fabricated to fit and will be removable and reusable. Insulation jackets will be provided for all pipe insulation in manholes and will comply with the requirements of the particular distribution system guide specification. Isolation flanges shall be provided when connecting to an existing cathodically protected heating or cooling distribution system or to prevent a new system's cathodic protection system from contacting an existing system. The isolation flanges will be installed in the valve manhole, and a typical flange detail is shown in figure 6.3. Figure 6.3 indicates a typical electrical isolation flange. Piping in valve manholes often will need supports within the manhole, especially when larger valves or equipment are attached to the piping. These supports will be located on the manhole plans as determined by the designer's expansion compensation calculations for each manhole, valving, and equipment layout. Valve manholes will be field constructed of reinforced concrete conforming to the current criteria. Valve manholes will be constructed of 4,000 psi minimum compressive strength concrete. Reinforcing bars will conform to ASTM A615 grade 60. Concrete floor slabs and walls will be of sufficient weight to prevent flotation in high water table areas. Floor slabs will be sloped to the drain which will be installed in the floor slab. Concrete wall sections will be not less than 8 inches thick and must meet anticipated load and soil conditions. Side walls will be constructed in a monolithic pour. Water stops shall be provided at all construction joints. Do not locate valve manholes in roads or parking areas which create an inadequate amount of manhole ventilation and poor access. Valve manhole cover types discussed are raised solid plate, supported cover, and concrete. Raised solid plate covers are preferred for high temperature hot water and steam condensate systems installed in pre-engineered underground heat distribution systems. For shallow concrete trench systems, the raised solid plate cover's raised feature will interfere with the trench's walkway function. When the valve manhole cover must remain flush with the trench top, the supported cover is the preferred type. For the raised solid plate cover, ventilation openings are provided around the entire perimeter below the raised top. The height of the valve manhole wall above grade, 6 inches minimum, shall be sufficient to prevent surface water entry. The solid plate cover assembly is removable. The cover, constructed of aluminum, also provides sectionalized access for inspection and maintenance. Supported covers may be used for any distribution system discussed here. For pre-engineered underground or prefabricated underground heat distribution systems, design the cover to be at least 6 inches above the surrounding grade. When used for concrete shallow trench systems, the finished top will be flush with the concrete trench top. Required grates or other structural members used for supporting covers shall be of corrosion-resistant material such as aluminum or galvanized steel. A checkered plate cover should be installed over gratings or other structural supports in most locations to minimize the influx of leaves and other debris. The checkered plate is attached to the grating and it is removable. With regard to concrete covers, the use of concrete covers is discouraged, but if used, they must be used with 4x4 aluminum doors for any distribution system covered in this discussion. Concrete covers should only be used if desired by the user or if specific design conditions exist, such as below to above ground system transitions. When used for pre-engineered underground or prefabricated underground heat distribution systems, design the top of the concrete cover to be a minimum of 6 inches above the surrounding grade. When used for concrete shallow trenches, design the cover to be flush with the trench top. Concrete requirements for this cover are similar to those required for valve manhole construction. Concrete cover shall be provided with details for this cover. A disadvantage of concrete covers is the difficulty in providing ventilation. For concrete shallow trench systems, a single 6-inch gooseneck pipe will be used to allow steam to exit the valve manhole if a leak or excessive heat loss is present. Note that for shallow trench systems, the gooseneck will be installed off to one side of the valve manhole concrete top to minimize pedestrian traffic interference. For pre-engineered underground heat distribution systems, two 6-inch goosenecks will be used. One will extend below the top. The other will be similar but will extend to within 8 inches of the valve manhole floor on the opposite side of the manhole. Drainage of water from the valve manhole is mandatory for the successful operation and longevity of buried heat or cooling distribution systems. There are 3 types of valve manhole drainage systems described: gravity drainage, pumped drainage from a sump basin, and pump drainage from the valve manhole. The most cost-effective and lowest maintenance system is gravity drainage to a storm drain when location, depth of existing storm drains, and local regulatory requirements allow this possibility. Drainage lines will be 6 inches in diameter minimum and will conform to the latest storm drain criteria and will be sloped at least 1% minimum. Valve manhole outlet will be a floor drain with backflow preventer to prevent stormwater inflow from the storm drain. Note that valve manhole drain outlet shall be covered with a hat-type cast iron pipe screen to minimize the accumulation of trash over the drain inlet. Also, the manhole floor must be sloped toward the drain. For pumped drainage, a duplex submersible pump system installed in a remote sump basin may be provided. The sump basin will be located no more than 10 feet from the valve manhole. Drainage from the valve manhole to the sump basin will be similar to drainage to a storm drain, including the valve manhole floor drain. Discharge from the pumps can be routed to a splash block at grade or to an adjacent storm sewer. Design of the surrounding grade must ensure drainage away from the sump basin, valve manhole, and concrete shallow trench if used when discharging to grade. A power pedestal complete with failure warning light will be provided with each. A specification for the sump basin system can be included in the applicable manhole or heat distribution section of the contract specifications. The sump basin design has proven to operate well even in the colder climates of the upper tier states in the continental United States. It is also an excellent method to retrofit existing manholes that currently do not drain properly. The remote sump basin increases the life of the systems by removing the sump pump and pump controls from the hot, humid environment of the manhole. Also, pump maintenance will be done outside the manhole. The pumps are easily disconnected and lifted to grade. Another means to pump water from the manhole is to locate duplex sump pumps in the valve manhole. Typically, a 2x2 by 1 foot deep sump will be provided in a corner of the valve manhole. The duplex sump pumps will be installed to pump out of this sump. The control panel will be high-level warning light will be mounted adjacent to the valve manhole at grade. This keeps the electrical panel out of the hot, humid environment of the manhole. Pump discharge can be routed to a splash block at grade or to an adjacent storm drain. Electric sump pumps used in the valve manholes must incorporate the design characteristics. Note that life of the pumps are typically shortened when installed in the hot and humid valve manhole environment. With regard to valve manhole wall penetrations, a design must be provided for the distribution system wall penetrations. For a shallow trench system, the wall penetrations will typically be the same size as the inside dimension of the shallow trench connecting to the valve manhole. Structural reinforcement must be designed around this opening. Drainage from the trench will then flow into the manhole. For pre-engineered or prefabricated underground heat distribution systems, sleeved openings will typically be provided with an expandable seal between the casing and the pipe sleeve. Structural reinforcement must be designed to avoid contact with the pipe sleeve and water stop to prevent grounding of the system's cathodic protection system. Waterproof membranes will be placed in or below the concrete bottom slab and continued up the outer sides to the top of the side walls in accordance with the valve manhole guide specification. Regardless of the buried distribution system, pipe anchors should be provided between 2 to 5 feet of a manhole wall to minimize movement through the manhole. For piping which passes through valve manholes, anchoring on one side only is typically adequate. Anchoring piping on more than one side may restrict pipe movement and overstress the piping in the valve manhole. Anchors will typically be provided as part of the distribution system and will not be embedded in the manhole wall. However, if the manhole is used to support an anchor, the manhole must be designed to withstand the forces exerted by the system. Expansion compensation stress calculation will always be conducted to ensure proper anchor locations throughout the distribution system. These calculations must also account for the expansion in the valve manholes. Non-metallic piping must not be used in the same valve manholes as piping carrying higher temperature media that could cause the temperature around the non-metallic piping to exceed the allowables and potentially cause permanent damage to the non-metallic piping. In addition, chilled water systems with PVC carrier piping must never be installed in the same valve manhole with any heating system. Although it's impractical to cover all special considerations which arise in heating and cooling distribution designs, this discussion presents typical design problems and solutions associated with steam, high temperature hot water, and low temperature hot water and chilled water systems. First, steam systems. Trap selection. Steam traps are used to separate the condensate and non-condensable gases from the steam. Many types of traps are used on drip legs for steam distribution systems. Those trap types include float and thermostatic, inverted bucket, thermostatic, and thermodynamic. However, for buried heat distribution drip leg applications, inverted bucket or thermostatic bimetallic type should be the trap type selected. For drip leg applications where freezing is a consideration, thermodynamic type installed vertically or bimetallic thermostatic type should be selected. Trap sizing is important for obtaining an efficient steam distribution system. Condensation in the steam line is caused by heat loss from the steam line. Trap life will be shortened, function affected, and excessive energy will be wasted if traps are oversized to handle the higher initial startup condensate flows. Therefore, the traps should be sized for the condensate load seen during the distribution system's normal operation. Because the traps are not sized for startup loads, the bypass must be opened at startup to allow condensate to pass until the steam line has reached normal operating temperatures. The designer will calculate the heat loss and condensate flow for that particular design using a recommended method for determining condensate loads during normal operation. It's critical that the designer calculate trap capacity using the method for each trap station in the design to ensure proper steam system operation. In addition to trap capacity, steam trap type, differential pressures, and inlet pressure must always be provided on the contract documents. Do not locate steam trap legs with associated traps more than 500 feet apart. Drip legs installed vertically down from the steam pipe are used to collect condensate. Design all steam lines to slope at 1 inch in 20 feet minimum towards these drip legs. It's preferable to slope the steam lines in the direction of steam flow whenever possible. The steam trap line and bypass line are connected to the drip leg in an approved manner. The drip leg will be the same nominal pipe size as the main line up to a 12-inch line and will provide a storage capacity equal to 50% of the startup condensate load with no safety factor and 1/2 of an hour duration for line sizes 4 inches in diameter and larger, and 25% of the startup condensate load with no safety factor 1/2 of an hour duration for line sizes less than 4 inches. In no case will the drip leg be less than 18 inches in length or larger than 12 inches in diameter for all steam line sizes. The designer will calculate startup loads for drip leg sizing using approved methods. Valve and strainer sizes will match the line sizes on which they are installed. Pipelines to and from the steam trap will be sized based on calculated trap capacity but will be no less than 3/4 inch nominal size. If reducing fittings are needed at the trap inlet and outlet, eccentric reducers must be used. The bypass line will be sized to accommodate warm-up condensate loads. For steam systems with an operating pressure of 150 psig or less and pipe sizes 12 inches or less, provide a 3/4 inch bypass line. If the condensate return main is a low pressure or gravity flow type, the trap discharge line will be routed through an accumulator. The accumulator will lower the trap discharge. Temperature and minimize flashing when the condensate is introduced into sloped condensate lines, which are routed to receiver pump sets located in valve manholes. The pumps push the condensate back to the central plant in a separate pressurized condensate line. This type of condensate return system is referred to as a 3-pipe or pumped return system. If the system pressure is sufficiently high, it may be used to force the condensate through the condensate return system to the central plant. No accumulator is required for this type system, which is referred to as a 2-pipe system. Fiberglass reinforced plastic FRP piping is usually allowed for most condensate return systems. Since internal corrosion is a frequent problem in steel condensate lines, FRP eliminates this problem. However, the FRP materials cannot withstand as high pressures or temperatures as steel and often fail when exposed to these conditions. A common temperature in an FRP distribution piping system where damage will recur is 250 degrees Fahrenheit. Condensate temperatures may exceed 250 degrees Fahrenheit at the outlet of steam drip leg traps on steam systems that have pressures greater than 15 psig. In order to use FRP condensate lines in this case, a condensate cooling system must be employed. In this system, the high temperature condensate is discharged into a cooling tank where it blends with the system condensate. The blended condensate is then routed to the condensate main. The FRP or non-metallic pipe transitions to steel inside the valve manhole to avoid burying the transition point. Also, non-metallic piping will not be allowed in a manhole with high temperature hot water or high pressure steam systems due to the potential for this pipe being exposed to damaging temperatures within the manhole if the manhole floods or the carrier pipe on the heating system breaks or leaks. If anchoring of a non-metallic piping system is required at the valve manhole wall to comply with the distribution system stress analysis, the system is to be anchored at both of the valve manhole wall penetrations. Provide adequate piping bends in the manhole to accommodate the expansion between the two anchors. Steel straps and bolts will be sized to accommodate the axial force of that particular piping layout. These sizes will be entered on the detail. Also, valve manhole sizes must be large enough to accommodate the anchors and still allow for maintenance access. Pipe sizing is critical to proper operation of both the steam and the condensate return systems. There are several methods to size steam lines. One of the quickest and most popular methods is using pressure drop versus flow rate charts, which provide steam velocities based on the required flow and pressure requirements. ASHRAE Fundamentals Handbook chapter Pipe Sizing is a good source for these steam sizing tables. Recommended velocities for various system pressure ranges are 0 to 10 psig saturated 1000 to 4000 feet per minute, 10 to 50 psig saturated 4000 to 8000 feet per minute, 50 to 150 psig saturated 8,000 to 12,000 feet per minute. In addition, ensure the total pressure drop in the system will not be excessive. Steam pressure must be high enough at the end users to meet all special process requirements. As described previously, there are basically two types of condensate return systems used on central heating systems: the two-pipe system, which uses steam pressure to force condensate back to the plant, and the three-pipe or pumped return system. With regard to steam system material selection, valves for high-pressure steam systems, 125 psig or greater valves, will be 300-pound class and will have welded ends. Steam and condensate valves at lower pressures will be 150-pound class with welded ends. Valves on trap stations, including the bypass valve, will be 150-pound class with threaded fittings. All fittings in the steam distribution system, except as discussed for valves, will be welded except at equipment, traps, strainers, and items which require frequent removal. These items will be threaded or flanged. Steam and condensate piping will usually be carbon steel conforming to ASTM A53 grade B, type E or S. Steam piping will be schedule 40. Condensate lines will be schedule 80, as will all welded piping less than 1.5 inches. Sizing lines for high temperature hot water systems is similar to any water system, except at high temperatures water becomes less dense and less viscous, and therefore the mass flow rate of the system must be calculated considering the lower density. Usually temperatures are about 400 degrees Fahrenheit for high temperature hot water systems. Recommended velocities for various high temperature hot water flows are as follows: up to 10,000 pounds per hour, 1 to 2 feet per second; 10,000 to 30,000 pounds per hour, 2 to 3 feet per second; 30,000 to 200,000 pounds per hour, 3 to 5 feet per second, and beyond 200,000 pounds per hour. Use velocity to accommodate 0.50 psi per 100 foot maximum pressure drop. With regard to selection of materials for high temperature hot water systems, all valves will be 300-pound class with welded ends. Shut-off or isolation valves will be gate type. Valve packings must be capable of handling the pressures and temperatures associated with the high temperature hot water system. All fittings on high temperature hot water systems will be welded. The only exceptions will be specialty equipment such as dielectric flanges used to isolate the piping system from a cathodically protected system. Piping for high temperature hot water systems will be carbon steel conforming to ASTM A53 grade B, type E or S. All piping will be schedule 40 except for welded pipe less than 1.5 inches, which will be schedule 80. For low temperature hot water and chilled water systems, pipe sizing. The most efficient method of determining pipe size for low temperature hot water and chilled water systems is to use head loss versus flow rate charts, such as those found in ASHRAE Fundamentals chapter Pipe Sizing. These tables are based on 60-degree Fahrenheit water, so for chilled water pipe sizing, there is little error introduced using these charts. For low temperature hot water systems, the use of the charts does introduce some error. However, the error is on the conservative side, that is, the charts overstate the pressure drop of low temperature hot water. With regard to material selection for low temperature hot water and chilled water for valves, typically valves on either low temperature hot water or chilled water systems will be 150-pound class and will be located in the valve manholes. Ball valves provide a good means for line isolation. Although non-metallic valves are sometimes allowed for these systems, metallic valves should be used for durability. With regard to piping, the most common piping material used for low temperature hot water and chilled water systems are steel, copper tubing, reinforced thermosetting resin pipe, fiberglass, and for chilled water only, polyvinyl chloride and polyethylene. However, do not include non-metallic piping in the same valve manholes with high temperature hot water and steam systems. Chilled water lines using PVC piping must be installed in separate valve manholes since PVC can be thermally damaged at relatively low temperatures. Outside the manholes, a separation of 15 feet minimum must be maintained between pre-engineered underground high-temperature hot water and steam systems and PVC encased prefabricated underground heating cooling distribution systems to avoid thermal degradation of the PVC. And this brings us to the end of this brief introductory discussion of heating, ventilating, and air conditioning systems. The topic is much greater than we could even scratch the surface on in a presentation like this, but I hope that this has given you an outline that will now allow you to move forward and address HVAC issues on projects as they come across your desk. So with that, let me thank you very much for dropping by and letting me chat with you, and have a nice rest of the day.